Section 8-2 is on critical points and points of inflection. The objective of this section is to use the first and second derivative of a function to find the critical points and points of inflection. So we've used those two terms before, critical points and points of inflection, but we're going to see how we can use the first and second derivative to help us determine those. All right, so let's start out with a critical point. A critical point, by definition there, is a point C, f of c, on function f of x, in which f prime of c is equal to 0 or undefined. In fact, I'm going to underline undefined here because that's the part of this that's usually forgotten. So basically it's saying that if you want to find the critical points of a function, you take that function, find its derivative, and you set it equal to 0, or find where it's undefined. Now this applies to any function. So if you start out with function f and you want to find the critical points of f, then you take the derivative of f, that's f prime, and you set it equal to 0 or find where it's undefined, just like this says. On the other hand, if you start with f prime and you want to find the critical points of f prime, then you find the derivative of f prime, that would be f double prime, and set it equal to 0 or find where it's undefined, and so forth. So you can find the derivative of any function and set it equal to 0 or find where it's undefined to find the critical points of the original function. All right, so let's look at a sketch here of a function that has some critical points in it. Let's just sketch a function that looks something like this. So this graph has a couple of different features here. First of all, you hit a maximum right here, and you hit a minimum right there. A high point and a low point there on this function. And this would be where f prime of c is equal to 0 at these 2 points. And then you also have these endpoints, as well as this point right here, which is called a cusp, remember. And this would be where f prime of c is undefined. Okay, all of those are critical points of function f. I should label our graph here that this is function f of x. All right, so finding where the derivative is equal to 0 or undefined will give us all the critical points. The key there for us to remember in this sketch here is that you end up with critical points at the endpoints every single time. And that goes back to the definition of a derivative and the fact that it involves a limit of a slope, and because the fact the function doesn't exist on one side of that endpoint, you don't have a limit, so therefore the derivative does not exist. So you lose the endpoints in the process of finding the derivative, thus f prime becomes undefined there. All right, so those are critical points. The next two terms here for us are local maximum and local minimum, sometimes called relative maximum and relative minimum. We'll use the term local to describe these, but you should be familiar with the term relative, meaning the same thing. But a local maximum is a point cf of c on function f of x in which f of c is greater than or equal to f of x for all x close to c. In fact, let me underline this here, that it's less than or equal to, or it's greater than or equal to. It doesn't have to be just simply greater than. It could be equal to the values around it. So you find a point which it's greater than or equal to all the other values around that point on the function, and you have yourself a local maximum. Basically what we are doing is we are restricting the domain around some small region on our graph, and if we hit a high point in that region, we call that a local maximum. A local minimum, on the other hand, or relative minimum, is a point cf of c on f of x in which f of c is less than or equal to, and let me underline that as well, that it's not just less than, it's less than or equal to f of x for all x close to c. So in other words, if I find a point that is lower than or equal to all the other points around it, then I have myself a local minimum. And again, basically what we're doing when we say for all x close to c, we're kind of narrowing down or restricting the domain of that function temporarily and saying, let's just focus on this one small region here, and have we found a lowest point in this region, a local minimum. Now, along with local minimum and local maximum, we have what are called our global minimum and our global maximum. So our global maximum, also known as an absolute maximum, we'll use the term global, but those are other terms. That's another term we use to describe this. Global maximum is a point c f of c on the function f of x, in which f of c is greater than or equal to f of x for all x in the domain of f. Notice that's what changes here between the two. Now we're not just looking at one small area around some point c, but we're looking at all of the values of x in the domain, and this has to be the highest point of all of those. Okay, again, I'll underline the fact that it's greater than or equal to, so it's okay if it's equal to the other points around it, or equal to other points that have the same value, but it has to be greater than or equal to all other values of x in the domain. Now your global minimum or your absolute minimum is a point cf of c on f of x, in which f of c is less than or equal to, and again I'm going to underline that for us. That's not just less than, it's less than or equal to f of x for all x in the domain of f. So once again, we have to look at the entire domain of the function and find the lowest point. That is called our global minimum. And basically what you can do, we'll see a sketch of this in a second, once you find all of your relative maximums and your relative minimums, basically if you go through and you find the largest of those, that's your global maximum. If you find the smallest of those, that's your global minimum. All right, so let's take a look at a sketch of a function here that we'll use to illustrate this. Actually, one note here before we do that. A maximum or minimum point can occur at an endpoint. So as you work through these problems, be careful with those endpoints there. We just saw with critical points that your function becomes undefined there, and it turns out that you can also have a maximum or a minimum at an endpoint there. All right, so let's take a look at a sketch here of an example. And we'll just do something simple like this. And so let's say that we have this graph of some function f of x, we'll say. And you can see then that we've got actually several local maximums. We have a local maximum right here and at the endpoint. So these are some local maximums. We also have some local minimums. I got a local min right here, and I got a local min right here. Again, if you consider just a small region around those, that's the lowest point in each of those regions. All right, and then finally, global maximums and global minimums. Now that you have all those labeled, you can look at for the all these and determine the highest one. That's the global max. So this one right here is going to be the global max. That's the highest point. And it looks like this endpoint over here on the left is your global min. Okay. Global max, global min, local max, and local min. All right, the next term for us to talk about is a plateau point. A plateau point is a point cf of c on the function f of x in which f prime of c is equal to 0, but f prime of c does not change sign at x equals c. So a plateau point is a point where you hit a slope of 0, so your function kind of levels off there, but you don't change sign, so you don't change from increasing to decreasing like we would see with a local min or a local max. you get a local max when your function's increasing, then hits a slope of 0, and then decreases. Or I should say you hit a critical point, because it could be that your function's undefined there as well. But here's a place where the derivative is 0, but your derivative does not change sign, so your graph actually kind of levels off there. We'll look at a sketch of that in a second. We actually saw a sketch of a cusp here just a second ago, but here's our definition of a cusp. A cusp is a point C, f of C, on f of x, in which f of x is continuous, but f prime is discontinuous at C. And basically these are points where you see kind of a sharp change in direction there. It's not a nice smooth curve, but rather there's some quick change in direction, and that gives us a cusp as a result. All right, so let's draw a sketch of a function that has some of these features. So let's say that we've got a function that, let's say it starts out right here and will increase, and then I'm going to have a sudden change in direction right here. So let's say that it comes off in this direction, and we'll say that it has another sudden change in direction. We'll bring it up here, level off, and then continue up to let's say this endpoint right here. All right, so let's say that's our function. Now you can see a couple of different features on this graph here. First of all, I can see that I have a cusp right here where I had a sudden change in direction. And it doesn't have to be very dramatic there. Okay, right here we saw a really dramatic change in direction. We were heading down pretty steeply, and all of a sudden, boom, we switched direction, or heading upward pretty steeply. Okay, but these are cusps. Okay. And we had one plateau point. We saw our graph kind of level off right in here somewhere, and then continue increasing there. So this is what we call a plateau point. All right. And we'll label this f of x. So there's a sketch of a function with a couple of cusps and a plateau point. All right, the next two terms here deal with concavity. We call a function concave up if a function has the following here. It's a point where, or point C, f of C, on the function f of x, where the graph lies above the tangent line. Another way to describe that is it has a U-shaped graph. Okay, concave up. If you draw the tangent line and your graph is above the tangent line, you got a function that's concave up. On the other hand, concave down is a point C, f of C, on f of x, where the graph lies below the tangent line. Or if you will, it's kind of like an upside down U shape. And the next term for us is, once we know concavity, we can talk about where we have changes in concavity, and that's what a point of inflection is. A point of inflection is a point C, f of C, on f of x, in which f of x changes concavity. That's the key there. Your function actually has to change concavity. We'll look at the way that we actually go about calculating these points of inflection. But the key is that you have to actually show that your function changes concavity there. You go from concave up on one side to concave down on the other side, or vice versa. If your function doesn't do that, you don't have a point of inflection. All right, so let's take a look at a couple of, or at a function that has a couple of these features here to it. So let's start out right here, we'll say, and let's have our function kind of increase like this. Maybe we'll change direction and go up something like this. We'll come back down, and we'll do something like this. We'll say, we'll end it right there. Okay. First of all, let's go through and mark a couple of key points here for us. I can see that my graph starts out, it's concave down until this point about right here, and all of a sudden it changes concavity there. And then it's increasing for a little while here. It still is increasing, but all of a sudden about right here again, it changes direction, and it's no longer concave up, it changes to concave down. And then it continues being concave down until about right in here somewhere, we'll say. And it changes concavity again to being concave up. So these are points of inflection. So here's one, and here's the other one. Those are points of inflection. And then your graph changed concavity, so during this section right here, it's concave down. And during this section right here, it has that upside down U shape that's concave down. So that's here, and that's here. And then you can see in this section right here, it has the shape of being concave up. And in this section right here, it also has the shape of being concave up. So that's right here and right here. All right, let's talk about the first derivative and everything that we can tell from the first derivative. I guess I'll just go ahead and show all that. Here's what you can find out from the first derivative. If f prime is greater than 0, so if your derivative is positive, in other words, then f of x is increasing at x equals c. Now this is something we talked about way back in chapter 1. That when we were first calculating an approximation for an instantaneous rate using average rates, we were looking at that rate, whether it was positive or negative, to determine whether the object was increasing or decreasing, and depending on what we were working with as to exactly what that meant for that problem. But if the derivative is positive, then the function must be increasing. If f prime of c is less than 0, then f of x must be decreasing at x equals c. So those two are related there. Now if f of x is continuous at x equals c, and f prime goes from positive to negative at x equals c, then the point c, f of c, is a local maximum. All right, so let's talk about what that means there. First of all, you got to have a continuous function, and it goes from positive, f prime goes from positive to negative. So if f prime is positive, that means your function was increasing. And then all of a sudden, after that, it goes from f prime being positive to now f prime being negative, so that means your function is now decreasing afterwards. So we changed direction there. You were increasing up to a maximum, and then you decrease after it. On the other hand, the last bullet there says if f of x is continuous at x equals c and f prime goes from negative to positive, now the other way around, at x equals c, then the point c, f of c, is a local minimum. And that's because your function was decreasing. That's how f prime is negative. Hits the local minimum, and then after that, the function has to start increasing again. So f prime would become positive. All right, for the second derivative, if you look at the second derivative tells us concavity. So first derivative tells us about increasing and decreasing, and as well as helping us find maximums and minimums. Second derivative tells us about concavity. If f double prime is greater than 0, then f of x is concave up at x equals c. If f double prime is less than 0, then f of x is concave down at x equals c. So you can look at the second derivative and determine whether or not your function is going to be concave up or concave down. And finally, if f of x is continuous at x equals c and f double prime changes sign at x equals c, then the point cf of c is a point of inflection. So your function has to be continuous. The second derivative actually has to change sign. That's the key for concavity. If your second derivative was positive, that means you're concave up, and then it becomes negative. Now you're concave down, you change concavity. Or if it's the other way around, you still change concavity there. All right, so we can use those first and second derivative information to help us determine what our function is doing. So let's take a look at an example here, and they're going to introduce us to a new technique here that we can use to look at functions. It says, for example 1, for the function graphed in figure 8.2b, sketch the number line graph for f prime and a number line graph for f double prime that shows the sign of each derivative in a neighborhood of the critical point at x equals 2. On the number line graphs indicate whether f of 2 is a local max or a local min, and whether the graph has a point of inflection at x equals 2. All right, so let's take a sketch of this function. And we'll try to roughly sketch it here. It looks like here's 1, 2, 3. And so it starts somewhere down here at some endpoint. Starts to increase, almost becomes vertical, it looks like. And increases to some maximum there. So this is our function f of x. All right. And it says now for the function graph there, sketch the number line graph. So this is something new for us, but we're going to sketch the number line graph right below our function here. We're going to actually have two number line graphs that we sketch here. And it's easiest if you line these up, so that's why I'm graphing it right below there, so I can put these values right on my x-axis here. Turns out these are all critical values here for me. And basically on my vertical axis, I'm going to use that space to mark a couple of things. I'm going to use this bottom space to mark what is happening to f prime, and the top space to indicate what I know from f of x. And so if I look at my graph here again, let's go ahead and fill in what I know so far about this function. I can see that I have an endpoint on my function at x equals 1. So we're going to abbreviate that EP for endpoint. And I also can see that my graph actually becomes vertical at x equals 2. So at x equals 2, my derivative here becomes infinite. Notice that I'm in that bottom row there, that section about f prime of x. And then finally at 3, I can see that I have an endpoint there. All right, so let's mark what I can see actually from my graph then. If I go back up to function f of, or the top part here of my number line graph for f of x, I can see that I start out at an endpoint and my function is now increasing after that endpoint. So we draw a arrow that's indicating that it's increasing, an arrow that's heading upward. If I have a slope that's vertical like this, then I can put a vertical line there to indicate that it's got a vertical slope. And after that, I can see that my function is still increasing, so we draw a line going up like that to indicate my function is increasing. And then down for f prime of x, I again can tell that at 2 this thing was an infinite slope, so that's why we put infinity there above 2. But between 1 and 2, and then between 2 and 3, I can put in some more information with the fact that if my function is increasing, then I know that f prime must be positive. And again, my function was increasing from 2 to 3, so my derivative must be positive. All right, so that would be our number line graph for f prime of x. We'll do the same thing for f double prime, except we're going to put f double prime of x here, and then just f of x. Again, it's helpful if you line up these x values here along your x-axis here. The only values we need to indicate are our critical points, but it turns out all 3 of these are critical points. Now, because we had an endpoint on f prime, that's also going to be an endpoint that we're going to mark here at 1 and at 3. And because my first derivative was infinite at x equals 2, it turns out my second derivative is going to be the same there, infinite. And now if you look at the sketch of the graph that we have here, our graph starts out concave up between 1 and 2. So I'm going to draw a little curve there to indicate concave up, the little U-shaped curve. And then if you look at what's happening from 2 to 3, from 2 to 3 we are concave down. Okay. So if we fill in what that means about our second derivative, from 1 to 2, if our function is concave up, we just said that that means that our second derivative would have to be positive. From 2 to 3, our our function is concave down, so our second derivative must be negative. And then finally, I can see that at x equals 2, I change from being concave up to concave down. So that is a point of inflection for us. I'm going to write POI. The book uses just PI for that. You can do that same thing if you want to, but POI for point of inflection. And that right there is our number line graphs for our function f of x, our first derivative and second derivative number line graphs. All right, let's take a look at one more example. Example 2 on the next page there says the figure there shows the number line graphs for the first derivative and the second derivative of a continuous function. That's key, it's a continuous function. And it says use the information to sketch the graph of f if f of 4 is equal to 0. Describe the behavior of the function at critical points. All right, so let's sketch in what the number line graphs are. And we need a little extra room because they didn't tell us what function f, of course, was doing. We've got to fill that in. But they told us that, we'll say this is 1, 2, 3. And so they said that you have an endpoint there for f prime at 1. F prime is positive and has an infinite slope, then is negative, 0, and then negative. And so let's fill in what that means about function f. Well, first of all, if function f is increasing, excuse me, if f prime is positive, that means function f is increasing there from 1 to 2. From 2 to 3, I can see that my function is decreasing, but at 2 I see I have an infinite slope. So we draw a little vertical line there to indicate an infinite slope. From 2 to 3, I have a derivative that's negative, so that means my function is decreasing. At 3, the function levels off. We draw a little horizontal line to indicate that. And then from after 3, it continues decreasing after that. So we draw, again, an arrow indicating that it's decreasing. Now, if you fill in what that means about our function starts out at an endpoint and starts increasing. So this would actually be a local minimum that we have there. Your function was increasing, then at 2 it became infinite, and then between 2 and 3 it decreased. So that means we have a maximum right here. And then you can see how your function decreases. It levels off with a slope of 0 and decreases after that. So that's a plateau point. So we have a minimum, we have a maximum, and we have a plateau point all in this one graph here. All right, let's take a look at the second derivative. So for second derivative, they told us that you have, again, an endpoint. And the second derivative is positive between 1 and 2. You're infinite at 2, of course, since we're infinite in the first derivative, we're going to be infinite here as well. We're positive at between 2 and 3. It's equal to 0 at 3 and then negative after that. So now again, fill in what that means about our function f. So if we have a second derivative that's positive from 1 to 2, that means our function must be concave up. From 2 to 3, the second derivative is positive, so that means our function is concave up. And from 3 on, our function is, second derivative is negative, so that means our function must be concave down. And so let's fill in what that means there about our graph. I can see that at 3, for example, I go from concave up to concave down. So this is a point of inflection right at 3. However, at 2, you can see that you're concave up from 1 to 2 and then still concave up from 1 to 2, so you are not a point of inflection there. In fact, because of the fact that we are concave up on both sides and we changed direction there from our first derivative test, this means we're going to have a cusp actually here. So if you want to note that you've got a cusp at that point, that sometimes will help you in your sketch. All right, the last part of this is then to sketch our function. So I'm going to try to draw a sketch of this function. And they told us that f of 4 is equal to 0. So we'll use that as another point here to plot. So f of 4 is equal to 0. So as we go to sketch this thing, I want to sketch it in different color, so I'll mark that blue. I just got to make sure that I go through that point there. All right, so my function starts out at an endpoint at 1 and increases. I can see that from my first derivative. It increases and it's concave up. Now once I know that it's increasing and concave up, that it basically gives me only one shape that I can sketch here. So I'm going to start. I don't know exactly where this thing starts, but I'm going to just pick a point for it to start. I've got to be concave up and increasing from 0 to, from 1 to 2. And then at 2, I hit a maximum. My slope becomes vertical there. I have a cusp. So now I start decreasing from 2 to 3, and I'm still concave up from 2 to 3. So it's going to do something maybe like this, and it levels off towards a slope of 0 that I have up there. It has a plateau point there at 3. So it continues decreasing after 3. I change concavity there. I have a point of inflection and change concavity, so I'm now decreasing. So I am decreasing and have a point of inflection at 3. And that's not the endpoint, though. They told us it goes through that point, but they didn't say that's an endpoint. So this function continues like this. So this would be a possible sketch of what f of x looks like. That's just from our number line graph. All right, that's as far as we're going here with this first part of the section.